So the definition up here says that functions, if they are one-to-one, this is adding to our definition of what a inverse actually is, but if I call something one-to-one, then they have inverse functions, so that it says, what does that notation mean again? F, and then the circle in the middle? Of. So F of F inverse is how we read that F with the -1. So you might have seen it more familiar as F of F inverse of X. That's how we saw them the other day when we were talking about composites. So that's just a composite, Cameron reminds us, where we take the inverse and we plug it inside of the other one. Or you can do it in the other order. You can take the inverse and plug in the function. Either way, if you do a composite like that, it says you should get just a single, simple, little, tiny x. So we're going to talk about that a little bit. A box. Nice. Thanks.
Thanks.
I have no idea.
Finally came. I don't know. That's mine. She said read a Mrs. Mills classroom.
No, let's open it right now.
No, can't. So what's an inverse?
Yeah.
The opposite. So if I have a point at 2, 3. Yeah, the question is, what does that word opposite mean? An inverse, I will remind you, reflects over this special line. In order to reflect over that line, I would end up at 3, 2. So the inverse is, if the original is 2, 3, its inverse would be at 3, 2. And I could give you any point. So if I were to tell you there was a point on the original function at 0, 4, you'd tell me there was a point on the inverse at
4, 0.
4, 0. They just switch places, literally y and x replace. So that's what an inverse is. So if you know the function and you know the function's inverse as an equation, supposedly if you make composites out of them, then they actually just simplify down to the value of x. What's a function?
So I think a function is considered a graph that doesn't have an inverse. I don't think so.
Some functions, a lot of functions have inverses. That are now they all have functions, or sorry, they all have inverses. Let's say it right, yeah. They do all have inverses. It's just that not all of their inverses are functions. When I say function to you, in order to be considered a function on your very first day of Algebra 1, it does have to pass the vertical line test. So if I have to pass the vertical line test, that means that all of my x's, like 2, for example, is at 2, 3. There's only one y value attached to it. That's what it means to pass that vertical line test. So if we were to put it into our calculus language, we could say all members of the domain, because the domain are the x's, so all of the members of the domain have one range value, since our range is our y's. So that's our new definition of our function. Each member of the domain is attached to one member of the range. Now, if we're going to reverse all the domains and ranges, if we're going to reverse every point on the graph and turn it around, in order to be a function, that would mean that when they turn around, the opposite would have to be true. Can somebody think of a graph that if you were to reflect it across this line, it wouldn't be a function? What's it? A parabola. So he's thinking of a U-shaped graph. When I reflect it over this line, it ends up looking sideways, and it's no longer a function. Notice that when I reflect it, there are members of the domain that are now tied to more than one range value. They have a positive and a negative on this parabola. If you think about the original function, how could you have guessed that that was going to happen? It's still a function. Each domain has only one range. But how could you notice that this was going to happen?
Horizontal line test.
If you think about a horizontal, it had two different domains attached to that range, which isn't a problem to be a function. However, it does mean that it would turn around and have two ranges tied to a domain, since they're just going to switch dots. That's what it means to be one-to-one. So when we talk about a one-to-one function, it means that not only is it a function, but also every range has only one domain. Or I like what Victor said, actually. It passes the horizontal, too.
So what are the functions, actually, what are the graphs that aren't functions? So what's a parabola?
That isn't one-to-one. A parabola is a function, but it is not a one-to-one function. Y equals x would be a one-to-one function.
So 1-to-1, but they have to both pass.
They have to pass both types of tests to be one-to-one.
So then what's the plus minus square root of x considered?
It would be considered not a function. So if we defined it, we would have to define it as plus as a function and minus as another function. It is a type, that one is specifically a type of conic, since it's a parabola, and that you can have sideways parabolas like when we did our conic chapter, but they don't all have, like, they don't have a big overall category other than the fact that they are in the category of things that are not functions. Yeah. Because we don't worry about functions or things that aren't functions in most of our actual world. So they have to pass both types of tests. Okay? If you have a function, you should be able to prove whether or not it has this value. Based on this up here, these composites, you guys did some work with composites. So I'm going to give you a function, and I want you to think about whether or not it would pass these tests. X to the 2/3 power. What does it look like? Anyone know off the top of their head? You could graph it and see. But supposedly, if it is a one-to-one function, if we can take its inverse and make composites out of the function and the inverse that both come down to x, supposedly it is one-to-one. So we can test it without graphing it. Did you graph it, Connor? Is it one-to-one? Looks like what? A bird.
Yeah, like anything like this.
Like you know when you're a little kid and you draw birds?
Like this?
Yeah. Only a lot longer.
Nice.
Like it goes on forever and ever?
Yeah. I think it is. It looks like a bird.
Might be.
Like you know what your parabola was?
Mm-hmm.
I think it's almost like categories on
Okay. Let's go through and let's do this. So if I wanted to find its inverse, how would I do that? Okay. So I'm going to make this say x equals y to the 2/3 power.
Now you raise the x to the 3
Just the x?
y. Well, those are canceled.
So he's trying to get y by itself. He's choosing to raise this to the 3/2 power, because what happens when you raise it to the 2/3 power and then to the 3/2 power?
It's just
Yeah. So his goal was to get y by itself, and he did that. But if he does it on the left, he has to do it on the right. And so y, in the inverse, would be equal to x to the 3/2 power. So the inverse of the function is equal to x to the 3/2 power. It is actually a square root function. Now, what Connor saw in his calculator was two sides of it, because he was seeing the calculator was fine with graphing it, that original one anyway, was fine with graphing two pieces because it was still a function. If we wanted to look at this guy as an inverse and look at whether or not he's one-to-one, we should be able to show that the composites work, meaning, like Cameron said to us, we should be able to do f of f inverse and reduce it all the way down to an x. So I'm going to start with my f function. Whenever I get to an x, I'm going to plug this function in. It's supposed to be x to the 2/3 power. What do I get? If I do the other composite, meaning now start with the inverse. Whenever you get to an x, it's supposed to be x to the 3/2 power, but I'm going to plug in the function f. This is like those inverses I made you guys do last week, or those composites, I should say.
Isn't that just a test?
All it is a test to check to see if it actually is
To see if your algebra's right?
yes, basically. To see if this was working in finding my inverse. So by showing both of them, you're able to know that your algebra is right. Now, I picked a pretty simple one where hopefully we didn't make any algebraic mistakes because it wasn't a very difficult looking function. But it could have been any function. And sometimes when you're doing inverses, it is very tricky to get your inverse right when you're trying to manipulate and move things around. So all this does, it allows you to test it to see, which is what some of your problems in this section are going to ask you to do, is to verify, rather than finding the inverse, verify that they actually are inverses of one another. And so you can do that by doing the work we just did, showing me two different tests. You have to check both because it could coincidentally work in one and not the other. But if both of them happen to come up to just x, then that means your algebra was right, or the function they gave you was correct. If not, then that means they aren't inverses of each other. Sounds fun. Does sound fun. It's a little bit of algebra to play with, basically. It's going to get you a chance to work on some composites that are a little more complicated looking. There's not a lot of them. I want you guys to try them. I'm going to add them to our list.